Okay, so this is lecture 8, concept development stage, specifically evaluation and selection. So in this lecture, what we are trying to accomplish is we are in this point of design in which we have different concepts and we are trying to decide which one is the one that we are going to select to move forward with the development. So this is all information that is part of your textbook, specifically chapter 8. And these are the topics that we are going to cover this afternoon. We're going to look into evaluation and selection of the system concepts. How do you analyze the different alternatives? If you're familiar with operation research, how can that be a tool in terms of making your decision? How do you look at selecting the concept from the perspective of economics and affordability? Events and decisions for consideration, and finally, alternative concept development and concept selection. So let's start with the evaluation. So as I explained, when we were looking at one of the documents for the project report, you get to a point in which you're going to have different concepts because the functions that your system is going to perform could be accomplished with different type of hardware or software. So at the end, you might end up with multiple options for some of the things that your system must do. So that physical implementation of these functional approaches involve the examination of different technological approaches, which will end up having a multiple or diverse source of alternatives in terms of configurations for your system. Evaluating these different concepts or system concepts may also require some applied mathematics techniques to maximize the performance and to minimize the cost for the entire system. So let's say you have 3-4 different technologies for 3 or 4 different subsystems. Now the question is, how do you set up these different technologies in a way that the system will accomplish your goals? And once you do that, you have these different alternatives. How do you make an assessment in terms of performance and in terms of minimizing the cost to select the alternative that best fit your needs? So next topic is on alternatives analysis. So the full alternative space should be considered when evaluating the design elements. So again, this is based on the idea that you will have multiple options in terms of coming up with a alternative for specific subsystems or components for your system. So you have to consider how the design may be developed in order to effectively execute the functions. So some of the constraints that you will look into are in terms of performance. So how well is this system achieving the goals or the objectives for my problem? What is the cost, right? There's a significant amount of dollars in terms of the cost for these alternatives. And if not, then I can just evaluate in terms of the performance and also the schedule, meaning the time that it will take me to complete this development and achieve the operation phase of my system. So these are the 3 things, and I believe I mentioned this from day 1, that we have to trade off, basically looking to the trade-off of these 3 in order to come up with the best alternative. Yes. Good. So the predecessor system where one exists form one end of the spectrum to be explored, right? So how is my development better than this current solution? And if the amount of resources that I'm going to put into the development of a new solution creating that enough of a leap in terms of performance to justify that that development. So the predecessor system is typically what we are going to be used. Modifications to the current system concepts should first be explored with a view to eliminating these deficiencies. We can see this mostly on, let's say, any car company. You see that they will build a, let's say, compact car, and the next generation is basically the same car, but with some new, I don't know, maybe an improved engine, or maybe having a, I don't know, a space that is now a little bit bigger, or maybe better light materials, so the fuel consumption is not as much. But at the end, you know that most of the development is coming from the predecessor, unless a full revision of the car is being implemented. Like for Hummer, the new Hummer, right? It's like if you are old enough like me, remember the Hummers that were designed in the 2000, those were giving you 7 miles per gallon. And now they have a new Hummer that is electric, right? So it's now not even gas engine, is an electric car. So that's a completely different development. So what is the advantage? Easier to assess from the standpoint of performance, development risk, and costs that are on a radically different approaches. The disadvantage is that are likely to have severely limited growth in terms of potential. So the other alternative, instead of going from building from the predecessor, is to go in innovative technical approaches. These are concepts that are generally riskier and more expensive to implement, but offer large incremental improvements or cost reduction and greater growth potential. The preferred system is preference for system or subsystem may be set forth when a significant advantage or advanced development work has taken place and produced very promising results. Such work is often conducted or sponsored by the customer. Another justifying factor may be when has been a recent major technological breakthrough, which promises high gains in performance at an acceptable risk. So can come up with multiple examples in terms of technological breakthroughs. Again, going back to the car industry, hybrid cars were one of those big breakthroughs. And then you saw one car company starting the change or the direction, and then other companies trying to imitate that major technological breakthrough. The idea of a preferred system approach is that subsystem analysis can start building on this concept, thereby saving time and cost. So if you're going to build a hybrid car, then you know that you go around that technology in order to build your system. Performance characteristics. The derivation of performance characteristics through the exploration of implementation concepts can be thought as consistent of a combination of two analytical approaches: performance analysis and effectiveness analysis. Performance analysis derives a set of performance parameters that characterize each candidate concept. So, for example, if you're looking at improving checkpoint conditions in an airport, like you don't have to wait that long to get to your gate, you can set up performance metrics such as the time a customer waits to get through the checkpoint, the size of the queue that you observe at each time period, the number of people that you have running the checkpoint, and so on. Those could be performance metrics. Effectiveness analysis determine whether or not a candidate concept meets the operational requirements. And if it's not, how the concept needs to be changed to do so. So if you, for example, are setting up yourself to say, I want my customers to wait less than 15 minutes, and your concept or your system that you're proposing is not able to get you to that point, then you have to think about how effective is your concept and what are the things that you need to change in order to get to that point. The performance analysis part of the process is used to derive a set of relevant performance characteristics for each candidate system concept that has been found to satisfy these effectiveness criteria. Constraints. The interfaces and interactions with other systems or part of the systems place constraints on the new system, right? So if you, for example, going back to the example of the airport, you have to work with the airlines, right? You need to know, okay, how busy is this terminal? It's gonna be how many airplanes, how many airlines are gonna be using this terminal, how many flights are going to be landing and departing this area, how often, if there's any differences between the days of the week, in order to plan for your development, right? So it's not just a decision that I'm making as an airport, right? I need to consult with the users of the airport. This constraint may affect the physical form, the weight, power, the schedules, mandate tools, software tools, operating frequencies, operator training, and so on. If you only have, let's say you're designing for San Marcos Airport, where is mostly a private airport, right? You don't necessarily have to worry about the same things that you're worrying about if you're designing a checkpoint for Austin, which will require more resources, obviously. The immediate benefit of early attention to such problem is that conflicting concepts can be filtered out, leaving more time for analysis of the more promising approaches. So as you move forward, trying to address these constraints, this performance, the efficiency, what you're trying to do is to discard those concepts that might not be performing or don't have the effectiveness or are not satisfying some of these constraints. And then you focus on the ones that are more promising. Yeah, I'll give you some time to. I'll be posting the notes. So if you don't get all the notes, you'll get them after the lecture. Questions, concerns, comments. So again, what we are trying to achieve with this lecture is to give you some guidelines in terms of how do you choose between different alternatives. Now that you're sitting down, thinking about, okay, these are the functions for my system. These are the subsystems. These are the technology that I can use. I can configure. I can have an architecture for my system this way, and this way. So these three alternatives, which one is the best that I should move forward and recommend for development? Okay, so operation research techniques. So I think all of you, not all of you, mechanical engineering here. So operation research is one of the tools that we use to make decisions. I mean, it's not an industrial engineering tool. It's also used in management sciences and mathematics and so on. But it's one of the tools that industrial engineers use to make decisions like how to schedule production and how to assign resources to a particular problem and so on. So these are optimization techniques that typically seeks to minimize or maximize an attribute of the system. Like if you go back to the checkpoint example, you're trying to minimize the waiting time, right? So you are trying to make decisions that are going to minimize the wait time of your customers. Or if you're changing that attribute to the queue size, right? So instead of worrying about the cycle time, I want to minimize, or I want the queue size to be less than 10 people. So now your decisions are going to be based on that attribute, not on cycle time, but on the queue size. There are different type of models. There are models that are called multi-objective that will combine like cycle time, queue size, and other performance in order to make decisions. So those are a little bit harder to solve, but those are alternatives as well. So linear programming is a technique that may be used to find a maximum or minimum value to achieve the best outcome. So for example, maximize profits or minimize the cost. So again, the idea of this class is not to teach you how to formulate a model and how to solve a model, just to illustrate how this technique can be used, right? So again, what you're going to have is a model that will state an attribute that you are trying to use to make a decision. And then you have some constraints that are telling you any decision that you make has to satisfy these constraints. So even though you're trying to make that decision, you need to make sure that these constraints are satisfied. So this figure right here is showing an example of a linear programming. This is a problem that seeks to minimize the total number of systems to be used to satisfy all functions, right? So we are not specifying the system. We are just stating we have a set of functions here that are 1, 2, 3, 4, 5, 6, up to 10. These are my functions. Those are the functions that the system must perform. And then here we have a grid that is trying to select based on the systems available. They have system A, B, C, up to F. You also have information about the system, whether we use the system or not. That's a binary variable. The cost of each system. And then a 1 will indicate the system that the system can perform the function, while 0 indicates that no, it will not perform the function. So that's the grid that we have here is identifying which functions each system will perform. And then here we have the desired coverage that we want to achieve. So we want to make sure that we cover all the functions. And based on that, we will make the decisions. Sorry. We're talking for almost 2 hours in a row already. So we are trying to make decisions that are going to minimize our costs to select the system. So the objective is to satisfy all the functions while minimizing the total cost. Our constraint is to make sure that we have integer solutions and that we meet or exceed the desired thresholds. So behind this data, there's a model that will try to satisfy those constraints based on that objective, and it will provide you, if a solution exists, it will provide you with the best solution. And that's basically what the linear programming model is going to do. Other optimization techniques, the systems engineer can use tools such as this to perform what-if analysis at the early phase of the systems engineering life cycle in order to explore how the total system concept may look like. Decision-making is a quantitative technique to identify the decision space and the possible outcomes and likelihood of the decision path to occur. So if you remember your statistics, basic statistics class, you remember maybe, I mean, at least when I taught the class, I used to teach the students about decision trees. Any of you remember what what that is? Right, so that's a tool that we can use now. The idea is you have a probability assigned to going in one direction or the other. And then based on the branch that you select, you have performance, right? And then if you keep splitting, then you can use that information to find out what will be or estimate your potential outcome based on those probabilities. So in order to build those trees, we have to identify the decision space, all possible decisions, and the possible outcomes and likelihood of the decision path to occur. Using a graphical decision of like a decision tree may provide stakeholders with insight into what may be evaluated and considered. So you as an engineer, you will know what you're doing, but if you're presenting this to someone that is not familiar with your approach, you can present that tree with the information just to give them an idea how the decision is made. Decisions are developed to assist decision makers in identifying the alternative decision paths and evaluating and comparing different course of action. So this is what I refer to as a decision tree example, right? You have alternatives. Each one of them will give you an outcome at the end based on those probabilities. And then as you can see, for example, when you look at E1, the outcomes are 2, 130, but that likelihood of getting the hundreds is very small, right? So you have to take that into account. The probability is very low, whereas 0.90 has a higher probability with the lower outcome. So the concept utilizes probability theory to determine the value or utility of alternative decision paths. The decisions are depicted by rectangles and our letter A, B in this case. The events are depicted by circles and designated E1 and E2. In this example, each decision has two possible choices. Events have more than one outcome with probabilities associated with each. Finally, the value of each decision path is shown to the right. Value can be anything that represents the quantitative outcome of the decision path. This includes money, production, sales, profit, and so on. So based on this, which decision path is the best? Anybody tell me which one? What would you do? So remember, E1 and E2 are events, those you don't have control, right? But you have control between A1 and A2 and B1 and B2. Those are decisions. So in order to do this, you're gonna have to estimate the expected value for each event and then for each decision, right? So expected value of E1 will be 10 plus 27. So it will be 37. A1 will be 37. And then the other one will be a little bit more challenging. So I don't necessarily have so B2 is 40, right? So you can at least compare A1 and A2 and B2. So between B2 40 and A1 37, you know B2 will give you higher profit. So going into A2 will give you a better likelihood of getting a better decision. So at least you know that for sure you can make 40, right? If you go A2, B2. And so that's the utility of this type of decision tree. You can estimate what are the chances of you, but still that doesn't mean that you're gonna get 37, right? Like for some reason you end up getting that 0.1, you get 100, right? So that's the power of these probabilities, right? You have, assuming a higher risk, you can pay off, but if most likely it's going to be 30, so you're going to be losing money. Okay, so what is the answer of the question? Is right here. A1 yields a value of 37, A2 expected value of 42. So choosing A2 yields the greatest expected value. And here's the the solution, right? So you get 42, and 42 will be the best course of action. So worst case scenario, you do 40. Well, yeah. Best case, you go to B1 and your expected value is 42. Any questions? Okay, so economics and affordability. The three main segments of affordability are discussed. These are cost estimating and analysis, investment decision analysis, and resource efficiencies. So for the cost estimating and analysis, the most popular cost estimate is the life cost estimate, or LCCE, which provides a cradle to grave estimate. This includes the initial research and development, or RAD, production, operation support, and disposal costs. So you're basically making an estimate for the entire life of the system. The research and development include costs like equipment, personal facilities, and testing, production costs, everything associated with materials to produce the system, the manufacturing facility, the labor force, training, parts, and so on. Operation and support costs includes the operating and supporting the system during the employment. That again, personnel, maintenance, all those things. And then finally, the disposal costs. So how do you get your system out of production or out of functioning? And how do you restore that area back to where it was before you were building that system? Investment decision analysis. This is a cost benefit analysis. So if you remember your engineering economics, you should remember how to do this. So you're basically estimating the cost and how much of a benefit you will get, and then you compute that ratio. Nothing difficult, right? Will help the decision makers understand the implications of comparing different alternatives, like performance and cost, to help down selection or final selection decisions. Elements of a cost-benefit analysis include define the objective, right? So it could be a clear on what the desired outcome of the study. Understand the problem. This should bind the problem with both the performance as well the cost boundaries in order to develop a clear, achievable, and measurable goals. And then formulate assumptions and ground rules. Identify and examine the alternatives. Ideally, you will have a minimum of 2. And that's why I'm asking you to come up with at least 2 concepts for your development, in addition to the do nothing alternative. So if you go to the video, if you go to the template, you'll see those notes in one of the documents. And the future to be alternative that is proposed. This could be several alternatives that are under consideration. Develop cost and benefit estimates. This could be organized into monetary or non-monetary benefits. Monetary benefits can be categorized in 3 areas: cost savings, cost avoidance, and improved productivity. Non-monetary benefits can evaluate the system objectives, the criteria on how the system or the objective is satisfied, and the measures by which to evaluate the performance of the alternatives. This might be more oriented towards the performance rather than the monetary aspects. So for example, here, this is a non-monetary benefits example in which we are looking at optimizing the lawn care. The criteria is safety, suitability, and performance, and the measures are for safety, the safety scores, the suitability, human factors, and the supportability, and the performance is the time spent mowing the lawn. Okay, so this is again another way of looking at selection from the investment analysis. All alternatives can be compared and ranked relatively to each other to show the relative benefit to satisfying the objective. Scatter plot like the ones we have here in 8.6 show the comparison between alternatives in terms of benefits on the left side, right? So those are those percentages, and the net cost savings in terms of money per fiscal year. So as you can see, we have 4 different alternatives: the baseline, the alternative 1, the alternative 2, and the alternative 3. Each one provides some level of benefit and also some level of net cost saving. The lines are showing the variability or the error bar that indicate the uncertainty in the calculations, or show the range of performance and the cost to the decision makers. So for example, if you look at that, alternative 3 is the one that's showing the highest net cost benefit savings. If you look at the variability for that horizontal line, it's big, like it's wide, right? But it never overlaps with the closest one, which is alternative 2, which means that it doesn't matter where that line or that point, and like that point can go, the real point or the real performance could be anywhere between this line or these 2 parts of the line. But it doesn't matter where it lands. If it lands here, it's still better than this other alternative. So in terms of net cost benefits, alternative 3 is good. However, when you look at the benefits, that has a wide variability. And if it lands here, that's the worst performance among the 3 or the 4. The baseline is not giving you a lot of net cost savings, but in terms of benefits is high. And then basically what you're observing is this one gives you a little bit of improvement in both. And these other 2 have more risk, more uncertainty, but are capable of providing you with better net cost savings. (8.6) Alternative concept development and concept selection. The decision in the process of concept definition center on the selection of a particular system configuration or concept and the definition of the functions it is to perform. The system engineering method calls for such decisions to be made by a structured process that considers the relative merit of a number of alternatives before any one is selected. This process is called the trade-off studies or trade-off analysis, and is used in decision-making processes throughout system development. So if you go back to what we discussed on Monday, in terms of the document that I show you, the different concepts, you had to evaluate those different concepts using a trade-off, right? So we can use the predecessor system as a baseline. In case where functions of the current system are the same or similar to those of the new system, the current system provides an arrow point of departure or system concept definition. A set of alternative approaches will begin with a minimum modification of the system restricted to those subsystems or major components that are clearly deficient. Right, so if that's the case, if you have a predecessor, most of you, I think, somehow can set up a predecessor for your projects. Maybe there's no a structured system, but you know what they do currently to address that problem. And then I am assuming that you are taking that as a baseline to make improvements. Some new system developments are driven more by advances in technology than by operational deficiencies in the previous system. Such advances are often incorporated into an existing system to achieve a specific performance improvements. Like I remember blockchain, one of the projects implementing this advances in technology that are helping to make things faster, better. If their impact is major, the possibility of a radical departure from previous configuration should be included among the alternatives. Original concepts, rare instances, a really different concept is advanced to meet an operational need, not likely to be a previous system to use for comparison, and then different type of alternatives will need to be examined, right? So in rare instances, you will have something that is coming from nowhere, right? To solve this problem, and then you create something out of nothing. So for example, the first attempt of creating a social network, online social network, right? So that was, it was actually, nobody thought about it in terms of a problem, but was radical, right? So often think about Facebook, but Facebook was not the first one. There was a lot of them that came before that, just they did it differently. But the original concept was a major revolution in terms of creating something original. The objective of trade-off studies in the concept definition phase is to assess the relatively goodness of alternative system concepts with respect to all these three things, plus the risk, right? So it's not just the cost, performance, and the schedule, but also how risky it is to develop. The results are judged not only by the degree to which each characteristic is expected to be achieved, but also by the balance among them. So we talk about trade-off analysis in one of our previous lectures, and we talk about how you compare two alternatives first, then you discard one of them, you bring the other one, you compare, and you discard one, and you keep that one that is, well, typically those comparisons are done in pairs. The assessment of risk is another primary systems engineer task, estimating the probability that a given technical approach will not succeed in achieving the intended objective at an affordable cost. Risk can be considered to consist of two factors: probability of failure and criticality of failure. So for example, could be one of the components that you're designing that has a very high probability of failure, but if it fails, you have an alternative that will work. It doesn't matter. You can still continue with your development. That's the criticality of the failure. Even though the probability is high, you know that if it doesn't work, you have an alternative solution that can help you move forward. However, if you are just relying on that development, the probability of failure is high, but there's no alternative besides that alternative, then the criticality of that failure is very high. So you have to make sure that you take that into account. You're putting all the eggs on one basket, basically, or you're trying to make sure that you have an alternative design in place in case that doesn't work. Combination of the probability of failure weighted by its criticality to the system. Conditions that may result in a significant probability of failure. A leading edge on proving technology is to be applied. A major increase in performance is required. A major decrease in cost is required for the same performance. Significantly more severe operating environment is postulated. An unduly short development schedule is imposed. Okay, so all those things are gonna make the criticality and then selection strategy. So this is coming straight from your book. I decided not to edit this. I think it was very relevant in terms of a step-by-step process for selecting your strategy. These are the following suggestions can serve as a checklist to be applied when appropriate. So I'm not gonna read through the whole thing, but this is something that you should consider when you're looking at deciding which concept to move forward with in your development. First stage of make sure that you have a sufficient number of alternative approaches are considered to address all the needs and explore all relevant technical opportunities. If the number of alternatives is larger than can be individually evaluated in detail, perform a preliminary comparison to win now out the outliers. So this basically you can sort based on specific characteristics and decide on, okay, I'm going to look into the top 5 of this list. Then check on the list of performance and compatibility requirements and select a subset of the most critical ones that are also the most likely to reject unsuitable concepts. Include consideration of growth, capability, and design margins as appropriate. Next, you look at the compliance, which is select the criterion. So basically, those tables that I ask you to work on, these are the functions, these are the requirements. How good is my system in terms of meeting the requirements? What subsystems are being connected to my functions? What type of technology will be used, and so on. Number 5 says assign weighting factors or priorities to the evaluation criteria, including cost, risk, and schedule, and apply to the rankings of each concept. Avoid concepts that do not have a sound balance of the above factors. And for each evaluation criterion, rank order the several candidate concepts, look for and eliminate clear losers. Unless there is a single clear winner, perform a significantly more detailed comparison among the 2 or 3 potential winners. To this end, develop a life cycle model for each concept, along with a work breakdown structure and a risk plan.